All right, so welcome back to the second day of the workshop. So the first talk is going to be given by Dr. Aradhana Singh, a faculty member at the Department of Physics, IISER Tirupati. Now, in case you're wondering why is she giving an online talk, actually Aradhana is currently in the US, so unfortunately she couldn't give this talk in person, but very kindly she agreed to give this talk online. So Aradhana did a PhD from IIT Indore, where she worked on complex networks, specifically spectral properties of complex networks. And she went on to do a postdoc at this institute and then in Israel. Can you just tell me which group, Aradhana? I've forgotten.
This with the group of Professor Baruch Barzil
Right.
and Professor Ivan Kohania.
Right. And then she joined IISER Tirupati about a couple of years back. Is that right?
Yeah, it's been more than 2 years.
Yeah. Okay. All right. So Aradhana works on several very interesting problems involving networks, including that of the Sinohabditis elegans, so which is this worm whose entire nervous system was the first to be completely mapped out. And it's a pleasure to have her give a talk on her work. So, Aradhana.
Yes. Thank you so much, Professor Tabra, for introducing me and also giving me a chance to speak in this conference, actually the workshop. So, yes, I would start now with this good morning. Good morning, everyone. I'll be presenting functional connectome, like some understanding, some ideas about the functional connectome and few understanding on it. So with that, first I would like to state this quote, which says that ask not for what the brain can do for computers, ask what the computer can do for the brain. And this is actually what is the main theme behind the network neuroscience, which is the essence of this workshop. So, like, we work a lot for the computers, and now the computers are working a lot for our brain to understand them. Because when it is the networks, and that too about the uh, brain networks, this the study cannot be done without the computers. So with that, I would proceed and I would introduce networks because it's the basics. So you all must be already knowing networks is the collection of the essentially two components, the nodes and the vertices. As this schematic shows, the red circles are the nodes and the lines are connecting them are the connections, which could be different based on the different type of the networks. So in general, we can say that nothing in this world exists in isolation and networks are everywhere. Like we can see networks in the ecological systems, in the transport, in social networks, in internet, and of course the brain. So when comes network, the graph theory is best used to study the networks. And in that, the networks can be represented by an adjacency matrix of which the each element is given by a weight Wij. And if a node I and j are connected with the weight Wij, the weight is given, otherwise it is 0. A network could be binary as well, where there are no nodes, no weights, and in that case, all the weights are 1. And it could be both the directed as well as undirected. So directed means only node 1 is influencing node 2, vice versa is not true. Whereas in case of undirected, both the nodes are influencing each other. So when about the connectome? So connectome is basically a complete description of structural connectivity, the physical wiring of an organism's nervous system. This was the basic definition given by Olaf Spawn in 2010. Actually, the connectome word was coined by him, and so far he has published most of the papers in this field. So connectome could be structural as well as the functional. The structural connectome maps anatomical connectivity based on the isolated specific fiber tracks, And the methods to study are the parcellations of the brain volume or diffusion tensor imaging. Whereas the functional connectivity maps the functional connectivity between the different brain regions, which is actually the spontaneous activity, which is correlated in some way. And the methods are neuroimaging toolkits, mainly this fMRI, EEG, MEG, and PET. So here I am talking mainly about the functional connectome because in my last talk in the workshop, I had talked about the structural connectome, and I am now interested mostly in the functional connectome. So I wanted to share my ideas here about the functional connectome. So when it is about the functional connectome, it's mainly the understanding of studying the time series. And how these time series happen. These time series are actually the activity of the brain, which is characterized by the electrical signals that happens through the excitation of the neurons. When the neuron fires, an electrical current cascades down the cell. And when numerous of neurons fire simultaneously, sensors on the scalp can perceive this voltage shift, a mechanism that underpins the EEG, and the range of this voltage signals is of the order of microvolts. They often referred as the brain waves. So you can say that this activity, the voltage that we have recorded are the brain waves. Also, like there is a change in the blood oxygen level dependent, and that can also be measured by fMRI, another different technique to study the functional brains. fMRI has a good spatial resolution, but it lacks in time resolution, whereas EEG lacks in spatial resolution because it's recorded from the surface of the brain, and but it has good time resolution. So they have a different utilization when it comes to the question. Like if you have to study the resting state, maybe the fMRI would be the best. But if you want to study the behavioral changes or the changes in the functional connectivity in a task, then EEG would be better. So the brain wave have different patterns. It could have frequencies of different range, and these are well known. The first one is the delta wave, which has the frequency in between 0.5 to 4 hertz, and it corresponds to like the deep sleep, actually the dreamless sleep, and where we don't have any awareness. And another is the theta, which is 4 to 8 hertz. This corresponds to actually this not the deep sleep, just before the deep sleep, like when our eyes are moving and we are dreaming. And then is the alpha band, which is about 8 to 12 hertz, and it is about the resting state when we are awake but we are not active. And then the beta waves, when we are active, actually we are alert. And the gamma waves, which are from 32 to 100 hertz, which are basically when we are highly active and we are doing multiprocessing. So why studying the functional connectome? Because the network-based evolution of the functional brain can provide, clinically more advances or the ideas about the pathological brain, and also it can be support, like it could be used for the diagnosis of the different diseases, neurological diseases. And also you can understand like how the decision making or the memory formation is happening in the brain. So when it is the functional connectome, then how to construct the functional connectome? So it starts with recording the signals, the time series, and then to find out the correlation between the different time series. So the like when constructing a network, the main thing is you should have two components. One is the nodes and another is the connection. So in case of the functional connectome, the nodes are the different brain regions, also known as the region of interest, and connections are the functional correlations or the coherence between the brain regions. So like here in this small schematic, that A, B, and C are the three time series, and we can construct the network and the corresponding adjacency matrix by calculating the coherence or the correlation between these three electrodes. And in doing so, like we can calculate either the statistical dependencies or the causal interactions among the various units. So when about constructing the connections, there are different methods, and the simplest one and the most used one is the correlation method. And this method is basically defined by measuring the Pearson's correlation, which is this cross correlation between the different time series. It is mainly defined in the time domain, and it gives the coupling between the different brain regions. It's undirected. It gives undirected functional connectome. And then another is the mutual information, which quantifies the shared information between the two variables, and it gives the coupling and undirected functional connectome. It can be defined both in the time as well as in the frequency domain. And this is the simplest method to find out the mutual information, which is on the Grasberger method. And third one is the phase synchronization index, which basically measures the synchronization between the different time series, and that you can find out using the Hilbert transform of the given time series, and then constructing the phase from it, and then calculating the phase blocking value, which is defined as this. Next is the coherence, which is a spectral representation of correlation in frequency domains. It is mainly defined in the frequency domain. It captures how strongly two signals co-vary at each frequency, and it gives coupling. It could be both directed or indirect based upon how you are constructing it. And then another two methods basically gives you the causality. These are the Granger causality and the transfer entropy, and because these are based on the causality, they are directed. So, because there are so many methods, the natural question arises that which method is best. So in that, the V. Chang et al. Reported that the mutual information was a better quantifier when they were studying the architecture in the brain architecture in the children with epilepsy. However, in most of the cases, it has been shown that the simple linear correlation are sufficient enough. However, because the connectivity matrices are in general affected by the volume conduction effect, mainly in case of the EEG, because the recordings are done on the scalp. So in practice, it is more appropriate to perform a thresholding to find out the correct and the meaningful connectivity. So what we are doing, we are first calculating the correlation matrix, then binarizing it by putting a threshold to get a functional network. So what are the different thresholding methods? The simplest method is the absolute thresholding, and it is simplest, you give this threshold, suppose you said W is a threshold, this TH is a threshold value, and if any connection is having this value or greater than this value, then that connection should be there, and otherwise it should be 0. So this is simplest, but there is a problem, how to decide that what threshold value we should choose. So in doing so, the largest connected component, which is the percolation based thresholding method, could be useful, which is about finding out the size of the largest connected components with respect to the threshold. So you start with the maximum threshold, and of course with the maximum threshold you won't get the fully connected network, and you keep reducing the threshold until you get the entire network to be connected. So that value you can choose as a threshold. However, in thresholding methods, there is a problem that if you are comparing the two networks, if you are comparing the resting state with the memory formation, then the absolute thresholding can give you two different networks with a different density. So the number of the connection could be different, and most of the network properties are biased by the number of the connections, so you cannot compare. So in that case, the proportional thresholding or the density thresholding is better, which fixes the density value. So here what you do, you say that I'll keep the top 10 or 20% of the highest connections, and rest of them I'll discard. So in this way, you are preserving the density so that you can compare. The another method to study for the thresholding is a minimum spanning tree, which is also considered as the backbone of the functional brain network, and which is on the idea that you are finding out the minimally connected network, means the cost is minimal, and because the cost is minimal, here the number of nodes are n and the number of connections are n minus 1. So there are different algorithms to find out the MST, and one of them is to start with the highest or the lowest connection based on what the connectivity matrix is, and then start adding the connections so that there is no loop. If there is a loop, you discard that connection, and in the end you get the MST. So when you get the MST, it could be path-like, it could be mixed, it could be star-like, and that could also be used to compare the given networks. Then the fifth method is the permutation testing, which is a statistical method, and in this method a null distribution of connections is estimated from the time series with the shuffled subset levels, and the correlation matrix is thus thresholded at a chosen significance level. So this null distribution is formed because from this shuffled subset levels, and then you compare it with the correlation matrix with this null distribution, and then you choose the connections those are statistically significant. Okay, so so far we have studied the method to construct the functional brain network, and in case you want to do so, the package which is useful for constructing the functional brain network is MNE. If you're working with the Python, it's an open source Python package which can be used for studying the MEG or the EEG and signals. And once this network formation is done, you have to study the network properties, and the network properties, for studying the network properties, you can use network X if you're using the Python, or you can use the brain connectivity toolbox, which is in MATLAB. So what are the different complex network measures which are useful for understanding the brains? So from the network perspective, the first fundamental and the simplest one is the node degree. It is the number of the links a node is having, and it also determines how influential a node is. So it is a measure of influence as well of the nodes, which could be very, very much important in case of the brain networks, because in brain we are interested in knowing that in different cognitions, which are the brain regions which are more dominating or more influential. And node degree is a local metric, like it is a property of each node. Whereas if you want to have some idea about the entire network, then you have to study the degree distribution, the distributions of the degree, how degree is distribution, and it will give you a global understanding of the brain. Next metric in finding this understanding the brain networks is the centrality. The centrality could be a different type, like the degree is also a centrality. The another one is the betweenness centrality, like how many times a node is there in the shortest path between a pair of nodes. And the closeness centrality, the nodes which provide the shortest path between the given pair of nodes. And the eigenvector centrality, which actually tells you that which node is more influential, like in a way that which node is more close to the hub, like here the red node and the gray node, the one with the arrow, both are having the degree 1, but if you calculate the eigenvector centrality, the red node has higher eigenvector centrality because it is directly connected to the hub. The next one is the participation coefficient, which tells about how much a node is participating in connecting the different groups. And then the page rank centrality, which is similar to the eigenvector centrality, but defined mainly for the Google search engine. Next, the network properties to study the brain networks are the clustering. Clustering could be global as well as the local. The global clustering is the number of the triangles that are existing in the network divided by total number of possible networks. And this is also called as transitivity because it determines how neighbors are connected. So neighbors of neighbors are connected. So next is the modularity. So modular networks actually have dense connection in modules and the sparse connection between the modules as given in the schematic. And modularity is defined as the fraction of edges that fall within the group minus the expected number of the edges within the group for a random graph with the same node degree distribution as the given network. And it can be quantified as follows. Next network measure is the path length and the efficiency. So the path length is about like how many step away you are from a node to the another node. Like from the node 1 to 2, there is one step distance. From node 1 to 4, there are two paths, and the shortest one is having the 2-step separation. Efficiency is directly correlated to the path length, like it's inverse of the path length. So the global efficiency is defined as the summation over the inverse of all the shortest path lengths. The other network features that are useful in understanding the brain are the rich club and the core. Rich club is the group of the nodes which are highly connected, the high degree nodes, and the core are the crucial hubs that integrate more loosely connected peripheral nodes, ensuring the efficient functional connectivity. Then to understand and to compare the functional networks, there are some null models that are used. First one is the regular network. The example could be the lattice, where there is only the connection between the neighbors, or the globally connected network, where there is a connection between all the pair of nodes. The most and the best used is the random network, where each pair of node is connected with the probability p, and it was introduced by Radosh, Paul, and Rani, like this method of generating the network. And the another null model for statistical validation is the small world graphs. The small world graphs were first, actually the existence of small worldness was first proved by the Milgram's experiment when he was sending the posts to the through the random people to particular person, and there it was found that the steps in which the post was reached to the particular person was less than the expected value, and that showed the existence of small world. Later, the Watson Stroges came up with a model that can give the small world networks, and as the small world networks are characterized by the higher clustering as well as the higher efficiency. If you start with the regular network and keep adjusting the connections, so rewiring the connection with the probability p for a given value of p, for a certain value of p, you find that the clustering is high as well as the path length is low, so the efficiency is high. That regime is called as a small world regime, and it is the small world networks. Actually, it is found that most of the real world networks are the small world networks. Next is the modular networks, for which the stochastic block models are used, and they're like the stochastic block models methods are basically the based on the probability of connection between within the group and between the groups, and these can also be stand as a null model to compare the functional networks. Next is the multilayer networks. Like as the name suggests, the multilayer networks has different layers, and it's a completely different paradigm because the multilayer networks are the network of networks, and to understand these networks, the supra-adjacency metrics can be used. So what is the understanding on the brain networks, the functional brain networks? first the brain networks are highly clustered. So we were studying the EEG signals, and we studied the clustering coefficient, and it was for the resting state, like resting state EEG signals. So we studied it for the, and we found that the clustering coefficient for the resting state brain networks was really very high. You can see this is the x-axis is the different subjects, and the y-axis is the clustering coefficient. The blue lines are showing the clustering coefficient for the average clustering coefficient for the functional brain networks, and the orange line is showing the clustering coefficient for the corresponding random network. And you can see that it's quite the clustering coefficient for the resting state EEG is quite high than the random networks. Similarly, the modularity is really very high for the resting state functional networks than the corresponding random networks. So see, here we are comparing with the null model, which is the random network. And this is the degree preserved random network, because then we are not changing the degree distribution and just comparing the connectivity. Next, the brain networks has hubs and are homophilic. Like if it's the average between the centrality of the resting state networks are really very high as compared to the corresponding random networks, and this shows the existence of the hubs, because if all the nodes had the same centrality, then the between centrality value must be same as the random network. Another is assortativity. The assortativity measures that how the nodes are connected, like the height and this. So the similar type of nodes are connected. Similar in the terms here, it is the degree. So the low degree nodes are connected to the low degree nodes, or the high degree nodes are connected to the high degree nodes, and we find that assortativity is really very high, which showing the existence of homophily in the resting state network, which is not true for the corresponding random network. And the another, so all these results, as well as it has been already shown that the brain networks have the small world feature. So what's the difference here? The existence of the spatial feature, like when the networks are spatial, there is a cost associated with them, like the regular cost, because it's a spatial network. You can think about the road networks, like the connections which are the roads comes at a cost, as well as the maintenance cost, like how much fuel it will require. Similarly, for the brain, it comes with the construction cost, means the white matter tract that has to be there. Also, the functioning of the brain, the metabolism. So the regular networks, which are the lattice, which have only the local connections, are least costly because they have local connections. But because they have only local connections, they don't have the long range connections, so they are not efficient. Whereas the random networks, because there are random connections, there are many long range connections, and they're efficient. But because there are many long range connections, they are also very costly. And the spatial small world networks lie in between, like they have moderate long range connections, which provide the efficiency, as well as have the segregation, which corresponds to the lower cost. So the same structural behavior has been replicated in the functional connectome as well. So these are the other results which show that the network topology of the functional networks, they changes when there is in case of the brain diseases. Like in case of epilepsy, it has been found that the global efficiency is significantly increased, and also the number of the functional connections increases. Similarly, the default mode network, which is this large-scale distributed brain network, which plays a critical role in cognition, including the episodic memory formation and monitoring the internal thoughts. Like it is actually indication of ourselves, like how we think about ourselves. And basically, DMN consists of all these brain regions. I won't say it, taking time. And it has been found that the DMN and the default mode network has been affected by the brain diseases, like DMN impairment are prominent in psychiatric disorders, also in depression. And DMN are also found to be particularly sensitive to Alzheimer's disease pathology, and which is affected by the loss of the episodic memory and relative cognitive functions. Also, one of the work shows that in the synchronization between the intra default mode network and the inter default mode network with the other part of the brain, how it changes in the resting state in the different frequency bands, and in the then there is some tasking state like the memory encoding or the memory recall when the subjects are given some tasks of recalling something or memorizing something. Then it has been found that this intra DMN has a higher synchronization in slow wave brain waves, slow brain wave, and in the other brain waves, the beta and the gamma, the synchronization between DMN and the other is higher. So it shows that because the earlier it has been shown, as per the understanding, that the DMN is have more DMN have more correlations in the resting state, but existence of this shows that the DMN actually is more synchronized at the slower scale of the brain in all the activities, serving as a backbone of the network function or the brain function. So, like there are other works also which shows that how the functional network changes in the diseases, mainly the Alzheimer's disease. So it shows that the individuals with the Alzheimer's disease exhibit degeneration of the specific brain hubs, reduces the clustering coefficient and the path lengths very close to the values of the random network. So it's no longer the small world, it becomes random network. The cognitive impairment in the AD was associated with the weakness in the modular interconnectivity. So modular organization is also get affected in AD. And also there is a global decrease in the long distance functional connections, of course, because especially between the frontal and the caudal brain regions. Then there have been alteration in the functional brain with respect to aging as well. So this work shows that the adjusted global efficiency remains same with respect to the age. There is no correlation. And there is the adjusted modularity. This is decreasing. Modularity is decreasing with the significance level and with the age. So the modularity is actually decreasing with the age, whereas the adjusted local efficiency is peaking at a certain age. So other works like where they have considered the multi-layer construction of the functional brain networks have constructed the multi-layer brain networks considering the time series in the different frequency domains, like all this the different frequency domain can be considered as the different layers. So we can calculate the similarity matrix for the different frequency bands and then construct a multi-layer functional networks by creating the supra-adjacency matrix, where D is the value of the interlayer connections. And here the challenge was to assign the value D, which was achieved through the classification problem, which you can study in this paper. Actually, I can tell you also in detail later on. And then about the multi-layer framework, The multilayer network for the functional brain network also can be constructed based on the time decomposition, like in the different time how they are progressing. And it has been found that the multilayer functional brain networks are more informative than the monolayer networks. So this group by De D'Amico et al., they calculated the sensitivity lasers in the different frequency bands, and they showed that the multiplex framework is more useful or more effective in classification of the healthy and the schizophrenic patients. So the accuracy was more for the multiplex networks than the corresponding monolayer networks. So when studying the functional connectome, the natural question arises that if there is any connection between the anatomical and the functional connectome, like the structural connectome and the anatomical connectome. And for that, few studies have been done, which says that this study says that like if you see the functional, the time series for this left motor cortex and the right cerebellum, this right motor cortex, they are quite correlated. But if you see the structural network, there is no direct connection between these two brain regions. Similarly, the primary visual cortex in left and the right hemispheres correlate in the function, but there is no anatomical connection. So one can say that no one-to-one mapping between the structural and the functional connectome exists. So with that, I would come to the future scope and challenges. So one of the challenge could be the generalization of the patterns or the reliability, because the functional connectome depends a lot on the individual genetics, development, learning, movement, etc. So it is very hard to find a robust FC. Like sometimes, like in AD also, there are many studies which say that in Alzheimer's disease the connectivity reduces. Some of the studies says that the connectivity increases. So there is no general perception. There is no general pattern. Also, the uncertainty in predicting the brain waves. Like in case of the adult brains, we can say that the functional brain network could be associated with the specific cognitive functions. But in case of the developing brain, there are no function specific hubs in the brain. The interpreting brain waves and understanding their correlation is challenging. Also, this field is in the fast transition, because every day the new technique comes and then it reshapes our understanding of the brain. But all this makes this field actually a long-lasting and vital field in neuroscience, because there is a lot to yet understand. With that, I would acknowledge first the organizers of this workshop, Shakti and Professor Sitabra, and then the funding agency DST, IC Tirupati, and all of my group members